You press the power button. A few seconds later, you're staring at a login prompt. Simple, right? But in those few seconds, your computer runs through one of the most carefully orchestrated handoffs in all of computing. A relay race where each stage does just enough work to pass the baton to the next. It starts with firmware, the very first software that runs when electricity hits your motherboard. Firmware hands off to the bootloader, which loads the kernel into memory. The kernel decompresses itself, initializes your hardware, and sets up a temporary file system called Initramfs. Once it mounts your real root partition, it launches PID1, the first user space process. That process, usually systemed, starts every service your system needs. And one of those services puts up the login prompt you see on your screen. Each stage knows just enough to do its job and hand off to the next. Let's walk through every step. The moment power reaches your motherboard, the CPU wakes up and starts executing code from a special chip, the firmware. This is the very first software that runs before any operating system, before any disk is read. The firmware's first job is the power-on self-test or post. It checks that critical hardware is working. CPU? Check. RAM? Check. Storage devices? Check. If something fails, you'll hear beep codes or see error messages. That's post telling you something is wrong. Now there are two types of firmware you'll encounter. The legacy BIOS, which dates back to the 1980s, and the modern UEFI. BIOS is simple. It reads the first 512 bytes of a disk, the master boot record, and jumps to whatever code is there. UEFI is far more capable. It understands GPT partition tables, can read fat file systems, and loads bootloaders from a dedicated EFI system partition. Either way, the firmware's final job is to find a bootable device and hand off control. The firmware found a boot device. Now it loads the bootloader, and on most Linux systems, that's GRUB too. GRUB has a clever two-stage design. The first stage is tiny, just a few hundred bytes that fit in the MBR gap or the EFI system partition. Its only job is to find and load the second stage. The second stage is the full GRUB. It understands file systems like ext4 and XFS, can read configuration files, and presents you with the familiar boot menu. GRUB reads its configuration from GRUB, CFG, which lists available kernels, their boot parameters, and the Initramfs image to load alongside them. When you select an entry or the default timeout expires, GRUB loads two critical files into memory. First, the kernel image vmlinaz, a compressed Linux kernel. Second, the Initramfs image, a compressed archive containing a minimal file system. With both loaded into RAM, GRUB's job is done. It transfers execution to the kernel's entry point, and the real show begins. GRUB just placed a compressed kernel image in memory. Now the kernel needs to unpack itself. The file is called vmlinaz, the Z stands for compressed. The kernel has a small decompressor built into its header. This decompressor runs first, expanding the kernel image into its full size. On a modern system, this takes a fraction of a second. But here's something surprising. Every x86 CPU, no matter how modern, wakes up in 16-bit real mode, the same mode used by processors from the 1970s. So the kernel has to walk the CPU through a series of mode transitions. First, from real mode to 32-bit protected mode. Then, from protected mode to 64-bit long mode. Each transition unlocks more memory addressing and processing power. Once in long mode, the kernel sets up its initial page tables for virtual memory, initializes a basic console so it can print messages, and begins its main initialization routine. The kernel is now running, but it still can't access your root file system. That's where the next stage comes in. Here's a classic chicken and egg problem. The kernel needs file system drivers to mount your root partition, but those drivers might live on that very partition. How do you read the disk when the code to read the disk is on the disk? The answer is Initramfs, Initial RAM File System. Remember, GRUB loaded this alongside the kernel. It's a compressed CPO archive that the kernel unpacks directly into RAM and mounts as a temporary root file system. Inside Initramfs, you'll find just enough to solve the problem, a minimal set of binaries, shared libraries, and kernel modules. Most importantly, it contains the storage drivers for your specific hardware. NVMe driver, it's in there. RAID controller support, in there too. The init script inside Initramfs runs automatically. It loads the necessary drivers, detects your root partition, and mounts it. Once the real root file system is successfully mounted, Initramfs performs a pivot root, switching the file system root from RAM to your actual disk. The temporary file system is then freed from memory, and the kernel continues with the real root in place. With the real root file system mounted, the kernel can now fully initialize the system. This is where things get busy. The kernel probes and initializes every piece of hardware it can find. Disk controllers, network interfaces, USB buses, graphics adapters. Each gets its own driver loaded. You'd see all of this as the dmesc log, hundreds of messages scrolling by as each subsystem comes online. Beyond hardware, the kernel sets up its core subsystems. The process scheduler decides which tasks run on which CPU cores. The memory manager configures virtual memory, sets up page caches, and initializes swap. The virtual file system layer mounts special file systems like proc, sys, and devtools, the interfaces through which user space will eventually talk to the kernel. The kernel also spawns its own internal threads, kthread, ksoftrd, quirker, to handle background tasks. But notice something important. Despite all this activity, there is still not a single user space process running. Everything so far has been kernel space. The kernel's very last act is to change that by launching the first user space process. This is the moment where the kernel crosses from kernel space into user space. It executes a program at sbin/init, and this becomes process ID1, PID1. PID1 is special. It's the ancestor of every single process on your system. Every program you run, every daemon, every service, they all trace their lineage back to PID1. And here's the critical part: PID1 cannot be killed. If it exits, the kernel panics and the system crashes. No other process has this property. Over the years, Linux has had different init systems. The original was sysvinit, which started services one at a time using shell scripts. Then came Upstart from Ubuntu, which added event-based triggering. But today, almost every major Linux distribution uses systemd. Systemd takes over as PID1 and begins orchestrating the rest of the boot. It reads its configuration, mounts file systems listed in fstab, starts services, configures networking, and works toward reaching its default target, which is the systemd equivalent of the old run-level concept. Let's see how it manages all of this. Systemd doesn't just start services one by one. It builds a dependency graph and starts everything it can in parallel. Every service is defined in a unit file. These files declare dependencies, what a service needs before it can start, and what it provides to others. Systemd reads all of these, constructs a dependency graph, and then activates services concurrently wherever the dependencies allow. The boot progresses through a series of targets. Sysinit, target handles early setup mounting file systems, setting the hostname, loading kernel modules. Basic target enables core services like logging and dbus. Multi-user target is where most of the action happens. It brings up networking, SSH, databases, web servers, and all your configured daemons. If you have a desktop environment, graphical target launches the display manager on top of that. This parallelism is a big reason why systemd boots faster than the old sequential sysvinit. Instead of waiting for each service to fully start before moving to the next, systemd launches independent services simultaneously. Services that depend on each other still respect their ordering, but everything else runs in parallel. One of the services that systemd starts is Getty, short for Get Teletype. Getty is the program that manages your virtual terminals. Getty opens a terminal device, like /dev/tty1, displays a login prompt, and waits for input. When you type your username and press enter, Getty hands off to the login program. Login uses PAM, pluggable authentication modules, to verify your credentials. PAM is a flexible framework that can check passwords against the local shadow file, an LDAP server, or even biometric devices. Once PAM confirms your identity, login sets up your session, loading your user ID, group memberships, and environment variables. Finally, login starts your shell, bash, zsh, fish, whatever is configured in etc/password for your user. And just like that, you have a fully interactive session. From raw voltage hitting the motherboard to a blinking cursor waiting for your first command, the entire journey took just a few seconds. Every stage did its part and handed off to the next. Let's zoom out and see the entire journey in one view. Firmware wakes up first, tests the hardware, and finds the bootloader. The bootloader, GRUB, loads the kernel and Initramfs into memory. The kernel decompresses itself, transitions the CPU through its mode upgrades, and unpacks Initramfs as a temporary root. Initramfs loads the right drivers and mounts your real root file system. The kernel initializes all hardware and launches PID1. Systemd builds a dependency graph, starts services in parallel, and brings the system to its target state. And Getty puts up the login prompt. 7 stages, each doing the minimum necessary work before passing the baton to the next. No single component understands the full picture, each just knows its own job and who comes next. That's what makes this design so elegant and so resilient. The next time you press that power button, you'll know exactly what's happening in those few seconds. It's not magic. It's a carefully choreographed relay race, refined over decades of engineering.